Hey everybody, Miss C here, and today we're going to learn about nuclear chemistry. We're going to look at their particles, and we are going to look at half-life. So when we're studying nuclear chemistry has to do with the nucleus of the atom. So nuclear chemistry happens in the nucleus. Now in our nucleus, remember we have protons and we have neutrons. And so I just went ahead and I drew that this is my nucleus and that I have protons and neutrons inside my nucleus. Remember P plus are the protons and N0 are the neutrons. Okay. There are a few different particles that we're going to use while we study nuclear chemistry. The first one is an alpha particle. It's a 4/2 He. So really it's a helium atom. And we call that an alpha particle. Then we have a beta particle, which is 0, -1 at the bottom, in E, because a beta particle is really like an electron. We have something called a gamma ray, and it looks like an upside down, or it looks like a Y here. It's a gamma symbol. Somebody could also draw it like that. Okay, and that's 0, 0, just energy. We have a positron, which is 0/1 E, and that's just like having just a proton, or similar to having just a proton. And then we have a neutron, which is 1, 0, N. We can have some different types of radiation depending upon what type of particle is given off in a nuclear reaction. First, we have alpha radiation. That's from alpha particles being given off. These are heavy short-range particles, which we can see from the high mass number here. These would be harmful if swallowed, inhaled, or absorbed in a wound. Okay, so radiation that would be bad for us if we ingested it. Beta radiation is from beta particles or electrons. These are light, short-range particles. It's basically an electron, and it can travel several feet, and it can penetrate the skin. Okay? Your clothing can protect you from some of the radiation, but it can, if your skin's exposed, it can get through to your skin. Then we have gamma radiation from gamma rays. This is highly penetrating radiation. That means that it can travel really, really far, and it can go straight through your body. To be protected, we have to use lead sheets. Okay, so if you go to the doctor and you need to get an x-ray done, then part of what they use are gamma rays and x-rays, and those travel through your body, and they show up white where they don't travel all the way through. And if you were to use a piece of lead, that lead, which is inside those jackets that you wear, that protects you and your other parts of your body from being radiated by the x-rays. We have something called transmutation. And this is what happens when a nuclear particle is absorbed or emitted. So it's the change in the number of protons or neutrons, right, are things in our nucleus of an atom, by either absorbing or emitting a nuclear particle to create a stable nucleus. Usually, things that undergo nuclear reactions are unstable, so they don't have the right number of protons and neutrons in their nucleus. So they will either emit or absorb one of these nuclear particles to become having a stable nucleus. There are 4 different types of nuclear reactions. We can either have natural or artificial radioactive decay. Natural radioactive decay is where a nucleus naturally absorbs or emits a nuclear particle, whereas artificial radioactive decay, a scientist bombards a nucleus with a nuclear particle. So something is done in a lab where the scientist either takes one of these particles and bombards it with a nucleus. Doesn't matter which one, but they do that to force the nucleus to break apart or to fuse together. We can have fission or we can have fusion. Fission is when a nucleus is bombarded with a nuclear particle to split the nucleus into 2 smaller daughter nuclei. And nuclei is the plural of nucleus. So splitting an atom is fission. Fusion is 2 atoms fusing together. So we can see here I have one atom that's splitting into 2 smaller atoms, which is the opposite of fusion. Fusion is 2 small atoms coming together to make one bigger atom. So 2 smaller nuclei are combined together to form a large nucleus. Okay, so fusion is fusing 2 small nuclei together. We can have some different causes of radioactivity. The first one is an unstable nuclei. This is because there's either too many or too few neutrons in our nucleus. For atoms with less than 30 protons, so it's less than number 30 on our periodic table, which is zinc. So things with less that are smaller than zinc, they need a 1-to-1 ratio, 1-to-1, of protons to neutrons. So if I have 29 protons, I need to have 29 neutrons to balance out my nucleus and for it to be stable. Atoms that are bigger than zinc, so atoms with greater than 30 protons, need a 1.5 neutrons for every 1 proton. So in order to get that, because naturally those elements usually don't, they're going to have to absorb or emit a nuclear particle, which will then result in a stable nucleus. So they're usually then absorbing or emitting a neutron, so that way they can get to a stable number of protons and neutrons in the nucleus. Now, when things decay or break down because of a nuclear reaction, we have a half-life. And half-life, you may have seen before as exponential decay. We may have heard it before in radiometric dating or carbon dating. Half-life is the amount of time required for half of our sample of a radioisotope, something that's radioactive, to decay. So we're going to go through a couple of example questions here where we have a piece of uranium, initially has a mass of 100 grams. After 5 minutes, how much is left if the half-life is 1 minute? Okay, that's a little easier to see. So again, piece of uranium has an initial mass of 100 grams. After 5 minutes, how much is left if the half-life is 1 minute? So if the half-life is 1 minute, that means, this should say 1. That means after 1 minute goes by, only half the sample is left. So every time a minute ticks by, half the sample has gone away. So if we start with, at time 0, my amount of uranium I have is 100 grams. 1 minute goes by, my sample gets cut in half. So half my sample goes away, so now I have 50 grams. Another minute goes by, half the sample decays away. Now I have 25 grams. Another minute goes by, half of it decays. Now I'm at 12.5 grams. And then it happens again, 6.25 grams. Happens again, 3.125 grams. And I keep getting smaller and smaller and smaller. I will never get to 0. And that's because you cannot have half of something be 0. So it will keep breaking in half and be smaller and smaller and smaller and smaller, but never actually go away. Okay, so an ultimate punishment would be, you can have the $1 million, but every minute you can only move half the way closer. At first you'll make some really big progress, but eventually you only go a little bit, a little bit, a little bit, but you won't actually get there. Okay, because let's say you couldn't reach out and grab it. We can also graph this information. When we graph it, time is our independent variable, right? We're controlling the time that we have. So time goes on our x-axis. The amount that we have is dependent upon how much time goes by. So the amount that we have amount of uranium remaining, and that's in grams. We should add in for time, that time is in minutes. Okay. So we have our two axes. We're going to have to come up with a title. We could say something that we know that this is radioisotope decaying, so we can call it radioactive decay. So we have the radioactive decay of uranium. Okay. We need to draw our lines for time and our amount. Time, we want the last time to be 5, and we go up by a minute each time. So we'll have, I'm going to switch colors here. We have 1, 2, 3, 4, 5. And then we know that we want the highest amount to be 100. And then half of it would be 50. I think I'm going to split those in half again. So it's going to be 25 and 75. Okay, so 4 lines there. We want to draw a dot plot and then a line of best fit. This is exponential decay, so it's not going to be a straight line. It's going to be a curved line. So we're going to end up connecting our points and kind of smoothing them out. So at 1 minute, at time 0, because we have 0 here. At time 0, I have 100 grams. I'm going to put my dot here at 100. After 1 minute, I have 50 grams. After 2 minutes, I have 25 grams. Well, that worked out well. After 3 minutes, I have 12 and a half. 4 minutes, I have 6 and a half. 5 minutes, I have 3.125, and then we don't have anything after that. So we can see that we have slowly gone down, but we have this curved fashion. And maybe you've talked about asymptotes, where there's an asymptote at 0, which means that we never cross our 0 line. We only just kind of keep going and we just skirt above it. Okay, but we never actually touch it. So this is called exponential decay. In our next example, we are going to look at the half-life of nitrogen-13 is 10 minutes. If I start with 2 grams, how much will remain after 40 minutes? I know that my half-life is 10 minutes. So that means every 10 minutes, my sample gets cut in half. My initial time is 0. And then every 10 minutes, I'm going to go through a decrease. I'm going to get cut in half. So I know that my timing goes out 10 minutes each time. Total time is 40 minutes. I start with 2 grams. So my starting amount is 2 grams. After 10 minutes, that gets cut in half. So I go to 1. After 20 minutes, total have gone by, so another 10 minutes. That one gets cut in half. That one gets cut in half again. And then we get cut in half one more time. So I can see that after 40 minutes have gone by, I've gone through 1, 2, 3, 4 different half-lives. It's been cut in half 4 times. So how much will remain? 0.125 grams of our nitrogen-13 remains. Okay. We're going to do one more example. Here we have an isotope. Our isotope decays to 25 grams in 24 seconds. I start with 200 grams. I want to know what's my half-life. So my initial time is 0. At the end, I get to 24 seconds. So some amount of time has passed. If I started with 200 grams and I end at 25 grams, I need to know how many times did my 200 get cut in half to get to 25. So my first one, half of 200 is 100. Half of 100 is 50. Half of 50 is 25, which is what I want to end with. So I end at 25. So I put this too far down. Okay. I know that when I've ended at 25 grams, 24 seconds have gone by. Now I need to have a number here and a number here. So I have 1, 2, 3 different half-lives. I've cut in half once, twice, 3 times. So that means from 0 to 24, I need 3 even increments. So 24 divided by 3 is 8. So every 8 seconds, this changed. So 0, 8, 16, 24. We're going to do more practice with this in class tomorrow. We'll also do a lab and you will take data, you will answer some questions about it, and then you will also make your own graph. As always, if you have any questions, please feel free to put them either in the comments, send me an email, or put them in the Edpuzzle. Have a good rest of your day. Bye.